Hello, it's James from XRobots.co.uk. This is part 1 of Robot X. At the end of my GONK Droid series, where I finally got this walking on a smooth floor, I mentioned what I was going to do next, and that was to build a robot which is basically modular and reconfigurable, and that's going to be the one for ongoing development. It's going to be made of some rather better materials. We'll do a little recap on that, but for the full explanation, check out GONK Droid Part 11, the second half of that video. So the basic plan is we're going to build a generic walking robot that's about 5 feet tall, and then we're going to do some mini-series after that to dress it up as different characters. And one of those is going to be Bender from Futurama. And then I'd like suggestions from you as to what other characters we should do, so feel free to put those in the descriptions of this video. So let's have a little recap on the materials, and then we'll get on with the build. I mentioned last time that instead of making all of the parts 3D printed, obviously this droid is going to be quite a bit taller, so the parts won't necessarily fit on the print bed anyway. We're going to use aluminium 2020 extrusion, and it's got these grooves in. You put a nut in, and you can bolt things onto it, and of course that makes it reconfigurable because we can slide them up and down afterwards and change the pivot points and easily change the structure. There are still going to be 3D printed parts to make brackets and so on, but the actual sticks are going to be aluminium. And in fact I found that 2 of these weigh the same as the equivalent length bit of 2x1 planed wood. So basically we might as well use the aluminium because it's far less bendy and it doesn't twist. These are the motors I used last time, and as I mentioned, as we scale the droid up, it gets bigger in 3 dimensions, so if it were twice as tall, it'd actually be 8 times the volume. So I'm going to use much bigger motors, and of course having bigger motors makes it much heavier as well, so there's more mass to move. We're making it about 30% bigger, but my motors are quite a lot bigger, and these are going to be drill motors driving lead screws or ball screws. I've got loads of these drills that basically are refurbs from Argos in the UK. They're cordless 12 volts drills. They cost about £15 new, and I picked up a job lot of returns which I can strip down for the motors and gearboxes. Obviously they have a chuck on them that I can stick a lead screw straight into, and they'll take quite a lot of beating because they're from drills. Last time I mentioned those are going to drive these ball screws, and these are basically, the nut here has ball bearings in that fit in the grooves so it runs really smoothly, and these are really efficient. These are a 12mm diameter, which unfortunately doesn't fit in the chuck. I could have them machined down, but I suspect they're made of hardened steel. These cost about £15 each in money with the ball screw and the nut. And to get ones with end machining, you can buy them. They're about £30 each. However, I found some lead screws which aren't as efficient because they just have a brass nut on. There's no ball bearings in there. But these are only £4.50 each, and these fit straight in the chuck. So these are still actually fairly free moving, and these are double the pitch. So this is an 8mm pitch, and these are a 4mm pitch. So this means that the robot will move twice as far for every rotation of the screw. Which is kind of good because it means it's more agile. These are also much lighter, so I want to keep mass out of the legs really. Even though it makes sense to have a fairly low centre of gravity, the legs still have to be quite agile so they move and they don't wobble against each other. So to start with, I'm probably going to use these lead screws, and of course we can reconfigure it all and change it for something better if it's worth the investment in the future. As I say, there will be some 3D printed parts, and I've been doing some investigation into other materials. So as you know, most of the parts I print are in standard ABS. This is 3mm blue ABS. There still probably will be some of this in there because it's quite stiff. But I've been looking at ColorFab HT, which is an amphora-based material which has no VOCs in. It's actually very, very good. It's very high impact. The layer bonding's really good, and there's no toxic chemicals that come out when you melt it, essentially. So I've been doing some little tests. You can see most of this roll's already gone. But I made a little bracket here, and it's incredibly tough. So this has been printed flat on the bed at the bottom here. So you can imagine that basically the layer lines go this way, and normally you'd expect this would be easy to snap if that was a pivot point. But on this piece, this is actually really tough. I can't break this. So basically, we're probably going to make loads of the high impact parts out of the ColorFab HT there. And of course, if I need to make any really stiff parts of the structure, we can use L brackets and things that attach to this extrusion to make angles if the 3D prints really aren't up to it. And we do need to keep this as rigid as possible. Obviously, we can just use any other generic brackets you can get from a DIY store and just bolt those on as well with the nuts that slide in here and bolts all the way through. So we should be able to make this really, really rigid. Here's my initial CAD for what the foot basically, and we're going to make that first and see how that turns out and see how it hangs together. So at the moment I've got these aluminium extrusions, I haven't drawn all the slots on them, and we've got these metal brackets which are the L brackets, which are the red parts basically. So obviously those are metal, we don't need to print them. These parts are going to be printed in the ColorFab HT as well as the pads on the bottom. So you'll notice I've got a rail here, of course there's a slot on it. So these things can be moved in and out to give it wider or narrower feet, or at least the contact points with the ground. They could also be changed in the future for pressure sensors or various different materials, but we'll print them in the HT for now. The main pivot sideways on the foot is going to be these. One is longer because it's at the toe end and the other one is at the heel end, and I've put a space in there for a captive nut so we can put a piece of 6mm stainless through and sort of screw that down at each end to hold it so it doesn't slip out. I'm using the standard settings in Cura from the drop down list on the basic page for that material, and it prints at 275 degrees with a 100-degree bed on the TAS. This is set up for the TAS 6, which of course auto heats and auto levels. So I've chosen a 25% infill, and if we just switch over to the layer view and let that render, we can see that's a sort of fairly tight infill, but it's obviously not really anywhere near solid, and that should be more than strong enough with the layer bonding we get from the HT. Here comes one of those parts. I'm printing this on a TAS 5 straight on the PE bed. It seems to be going pretty well. I'm printing at 50mm a second, which is the default setting, and that seems to give the best layer bonding. Here's one of the first parts appearing on a TAS 6. Don't know if you can see the infill there. I'm not sure if what you see in Cura is very representative of what you actually get. It seems to be less dense. I think the lines are drawn thicker in Cura than they actually are in real life. But anyway, that should be more than strong enough. I'm printing these pieces directly on the glass here, and I already took the PEI off so that I could print nylon on here. It seems to be sticking pretty well. I've used some Yoo-Hoo glue stick spread on there, and that seems to work okay. Haven't tried any larger parts yet. So these parts have finished printing. I've also printed similar parts for the other foot, so I don't have a massive printing backlog when it comes to it. I've got my captive nuts in there. You can just see there's a nut in the hole on both of them, and that hole is just the right size for some 6mm stainless that's going to go through and make the joint. So now we just need to cut up some extrusion and we can put that together. So this stuff is incredibly tough. It is slightly flexible, but I can't really bend that with my hands. It is slightly more flexible off the roll than ABS, but as I say, it's quite high impact, so I'm not finding or expecting any problems with layer debonding there. Pretty much within the load of the robot, so that should be pretty good. I need to cut the extrusion, but I don't own a miter saw, so what I'm actually doing is making a mark there with the scoring tool and drawing a line on, don't know if you can just see it, and then cutting it from all directions with a normal hacksaw basically. So cutting a little bit so that I get all of those straight and they meet in the middle, and I've done one already, which is this one. This is one of my hand cut ends. It's not totally perfect, but once it's butted up with metal brackets or 3D printed brackets or otherwise, of course that'll be fine because the strength is in this piece and in a 3D printed piece over the top screwed down. So I've cut all my extrusion. I want this to be really rigid, so I am going to use the metal brackets in the corners there, and then of course these go on top. So we probably could get away with some ABS corners on here, put on flat on the top and bottom, but I really don't want any flex in the feet. Some of the other parts where I really don't want flex either, I will do the same probably. But there we go, so we need to attach these down now. So we're going to bolt all this together with M4 hardware. These are socket caps that have a kind of Allen head on them. And also these T-nuts which slot into the slot of the extrusion. And these are drop-in ones. You can get some that you slide in and then you screw to. So these are slightly different in that you drop them in like so. And then as you turn them, the nut turns and that's then secure. So that can also slide up and down, so we can move the parts around if we need to. And if we need to take it out, we just turn it back the other way. and it comes out because it's that T shape. So let's get all that bolted together. Here it is all together, so it's looking pretty substantial. It feels incredibly rigid, and I can't flex that really, no matter how much I try that way. It's incredibly rigid with those corners and with the prints on top. I'm wondering how rigid it would have been just with 3D prints top and bottom, and we may do that with some of the other pieces so we can test it. It already weighs in at just over half a kilogram, which is 1.2 pounds, so fairly substantial compared to that plastic GONK Droid foot. So compared to a GONK Droid foot, that was of course just 2 bits of ABS stuck together. This is slightly longer, and it's actually currently where it touches the ground slightly narrower at the moment, but of course I can move this around. Just by moving these in and out, I can get the contact points with the ground in different places or add more, like I had in the CAD. I could also slide up this rail here, so I could make it wider on the outside and less wide on the inside, or I could put really big pads on here of different shapes and all sorts of things, so I can completely reconfigure it and test it out without actually doing too much in terms of making new parts. Here's the next stage of it. So we're going to build a tilting mechanism that tilts this way, and you'll notice that's a T shape, and that's so we can get the actuators down each side here, as I explained at the last part of the GONK Droid series, and hopefully we'll get time to build them up in this episode. So I've got a hinge point that goes across the bottom here. Again, this is all going to be bolted on with those T-nuts to the piece of extrusion, and a T shape here. Now I have put metal brackets in again, or left space for them, and I've also got this ABS bracket which is a bit stiffer than the HT, and that's just going to sit on the top, and we've got the HT in a T shape on the bottom there, so that should provide some extra rigidity, although I think the metal brackets are pretty strong. That also has the captive nut in, which is going to hold a 6mm stainless steel shaft to go all the way through those holes to stop it slipping out. And of course these parts again are HT because it's high impact, and we'll print those with this surface flat on the bed and this surface flat on the bed. So let's have a look at those. Right, here they are. They all look pretty good. These pieces saddle nicely onto that extrusion, so that works out. You'll notice there is slightly more flex in the HT parts than there is in the ABS parts, and you can tell by the sound they make that one is sort of harder than the other basically. So let's get that bolted together. We need to cut some extrusion, and that should sit nicely pivoting across here. Right, that is all together. It looks rather nice, and it's extremely substantial, so I don't know if I actually need the metal brackets, but there we go. So now we need to stick that on some 6mm stainless and make that pivot point. I've put my 6mm stainless in, and that's held with captive nuts at each end here so it doesn't slip out, and the shaft goes all the way through. You can just see a bit of it there. And now that makes a great pivot point, so now we can start working on that lower leg. So building up another stage here, we're going to put the lower leg on, and this is, again, you'll see this familiar parallelogram looking thing that we had in the GONK Droid, albeit in a triangle shape from the top, so we can get the actuators down in the 2 gaps. And again, just aluminium extrusion built up, some HT printed brackets there. And again, I think I'm going to use the metal brackets to hold this piece really rigid, and I'll probably put an ABS plate on there in blue just so we've got some more blue parts really. Don't know if it'll do much for the rigidity, but it's going to set it off and make it look really nice. And of course we'll then we've got these brackets with double hooks on, so again the upper leg will go on the top there in exactly the same fashion. Here they come. I'm actually doing these parts slightly denser because some of these parts are slightly thinner. Here's the next stage, so that is of course the same top and bottom, so we can hinge both the upper and lower leg. And it has those blue things again to hold those 2 shafts that go through for the hinge points. That's the formation for the front of the leg and a single stick at the back. We've got these parts here, they're slightly flexible, but once that's bolted onto the extrusion with a couple of bolts either side, it should be more than rigid, and because of the extrusion across here this won't twist, and we've also got a piece of 6mm steel going through those, so hopefully that should be perfectly good. Alright, so here it is in real life, so it feels extremely substantial. There's a bit of a squeak, which seems to be one joint. It seems to be the metal on the HT, or the HT against itself, so I need to adjust these spacings I think. It's only one joint that's squeaking, the rest are silent. Which is a bit annoying, but there we go, and obviously it leans that way as well, and the upper leg of course is just the whole thing extended, and I have printed a duplicate set of parts for the upper leg, but I don't have enough aluminium now to actually make it. But I don't have to go through that whole printing process again because it's already done. So let's have a look at the actuators, which go down the back here. A couple of adjustments and some lithium grease, and now it's entirely silent. So essentially I'm going to take this assembly and it's going to be coupled to the front here, probably on a varying distance of bracket, and back down to here, so it can pull the leg backwards and forwards this way and also push it sideways. And of course there's going to be one of these on each side, so when they both push, it pushes it forwards and backwards, and when one pushes and pulls, it moves the leg sideways like that. So obviously this lead screw is too long, it needs to be cut down quite a bit, but we need to have a bracket that will hold the motor so it can move all around, and the same for something to hold this nut. So essentially the nut can swivel all around on some sort of thing, and there's space for the lead screw to go through so it can pull and push. I need to make a bracket to hold the motor and allow it to swivel around in at least 2 axes. You'll notice there's some tabs on the motor here where it was originally fixed into the drill body. So I've made this test piece that does actually fit on there. It's pretty tight, but it does in fact fit, and you'll notice it's sloping down because this side is slightly thinner, so I probably need a little step in there to just ease that side up a bit and keep those two parallel. We'll just have something that clamps that in the middle and provides a pivot point. Essentially what we want is a motor either side of the calf there that has the spindle coming down and, as I say, coupling to the bottom. So we need somewhere to couple that. I've got this yellow part. This is going to be printed in the HT as well. I've just coloured some of the parts differently so I can see them for now. So there's a yellow part there which has 2 pivots with 2 captive nuts to hold some 6mm stainless. And attached to that are those green parts that can swivel around it there. And then attached to that is a clamp that holds the motor, and you'll notice I've drawn these so we have the step in the middle because one side is thinner, and those are bolted together with some studding through the 3 holes there, and as again 6mm stainless fits through there and is attached with a captive nut which is held inside. So if we just get rid of that, we can see there's a captive nut and another screw hole there to put a 4mm bolt in to hold that axis. So we're going to need some stoppers on the outsides of these to stop the thing slipping off, but we can deal with that afterwards. So I've laid out all the parts that need to be printed, which are down here. So we've got opposite sides for each side and the yellow piece. So we'll get those printed in HT and see that they fit. I'm printing these parts in about 30% infill, so they should be a bit more rigid than the other parts, but they are quite big chunks anyway, so they should be quite dimensionally stable. So my brackets are printed and I've attached those to the motors there. Obviously that one's up the other way. I've got these with the captive nuts installed, and I've put a little grub screw in there to hold that captive nut. So that's the other plate that goes on the front. Let's see where that fits. Okay, so that piece goes right in there, and it fits just between the nuts. I left clearance either side for the existing nuts, and it of course bolts onto the back there with some more of those special nuts that go in there and so on. So we'll get that bolted on and we can get it assembled. So those two are installed, and we just need to put a cap on these to stop these things pulling off, which I'll add on in a minute. So I've just hooked one motor on there for now. We'll see it moves this way and it can move this way. So I've got the switch and everything there for testing, but basically if the other end of this is coupled down to the foot, then as this moves forwards, it does this kind of thing, and to move sideways, there's probably not much pivot actually required in that axis, but the whole thing can move around, and there's obviously one on the other side that helps push it sideways as well. So the only slight thing is that this will collide with this when it bends its knee a lot, but that's pretty much the limit of the mechanism anyway. So I think that's all right, and I'm going to leave it at that. We do need another cap on the end there to stop this pulling off. But let's install the other motor, then look at the other ends where the lead screws are. So looking at the other end of the lead screw, it seems like I need about 100mm of travel, which means if I put the nut essentially, is going to go basically mounted on here with the 4 screw holes. It means that I need 100mm for that screw to disappear inside when the leg is back as far as it goes. In reality, it's probably not going to move that far for walking, but we need to allow it anyway so we can move the joint to the full position. So essentially we've got this tube with a hole all the way through the middle and the nut at the top, and that needs to pivot in 2 axes. So we've got another axis pivoted that way and another one lengthways through this assembly with this hole here. Now the issue is, of course, we need to have enough length of 6mm steel that we can keep that thing stiff. So within the red part there's another captive nut and a place to put quite a long piece of it before we get back into the other axis, but that does make this thing very long, so there is still possibility for flex in this. Obviously it's bolted to the aluminium rail at the bottom. The only thing that can really flex are the 2 forks on the side, So if this becomes a real issue, then I'll have to move this piece all the way out so that the axis actually comes down one side of this red thing. But that does make the ankle rather wider than I want it to be, and remember that's on both sides. So for now we're going to try it like that. The other possibility of course is to make that red thing a complete O shape and put another pivot point at the back by modifying this piece so that we can get another pivot point. But for now we're going to build this out, we'll see how much it flexes and see what to do really. So it's all going to be printed in HT. The layer bonding is more than good enough for this piece to be printed as you see it here, and that should all be alright. I've installed one of those there, and I've got the other one here, and this is printed with 6 perimeters, and it's printed with about 30% infill, and it's incredibly rigid, so I don't think I can snap that. I've screwed the nut in there, you can see, which is to the bottom of the lead screw, and of course the other end of the lead screw is installed there in the motor, so we just need to fit this on the other side and we can see what we've got. Right, here it all is together, so just ignore these wires at the moment. These are for the original drills, which I'll use for testing in a minute, but hopefully we can see we've got those 2 sort of pistons, if you like, at the back there, which are going to pull it backwards and forwards and left and right, and altogether it's pretty sturdy. There is one small issue that I'm not that happy about, and that's this here. So if I push this whole leg backwards and forwards, we can see there's a bit of play in it, and that appears to be actual wobble in these joints backwards and forwards there. So there's not really anything I can do about that now. I could have another nut at the other end, I guess, but when this is right out, the lead screw is right at the top, and when it's in, it's right at the bottom. So it's kind of hard to do anything about. The ball screws, there might have been less flex at that point. So there is a bit of wobble in the mechanism, but actually it's a hard stop once you hit it, rather than continuous bend of any plastic. So we can pretty much compensate for that like backlash in a CNC machine. What's supposed to happen, of course, with these lead screws is you actually mount them on a bearing and then have a coupler to a motor here, so the lead screw is suspended at both ends. Then the nut will travel up and down, and that should actually push some sort of carriage that's on some other rails. So you're not putting the force of the carriage twisting and turning on this actual screw and the nut. So that'd be a much better approach if I had space to build it, but for now I want to keep it really simple. And of course the other issue is that this pivot here is not completely on centre with the middle of this lead screw. It's actually slightly off centre, which causes this to bend around this as this pushes down off centre. So ideally, if it weren't for that, then this nut would push completely on the middle, and this thing would only be pulled up and down rather than being pushed over. So we may need to refine this in the future. The hips will be slightly different, but for now we're going to build it like this and see how much of an issue it is. So I've just attached the drill batteries to each of these on long wires so I can test the mechanism. Eventually it will be controlled from a central power source. It obviously won't be controlled with these switches, it will be controlled with a control system. Have a look at my GONK Droid project, it's going to be better than that. But for now I can just run the motors to see the motion of the lower leg here. So if I run both of these forwards, obviously the leg goes forwards there. If I run them both backwards, it will go back again. And of course it's both motors pushing and pulling, and that's going to be the main load that lifts the robot up. So if we just bring these forwards again a little bit, obviously we can see if we run one way and one the other way, we can pull the leg over to lean over, and of course we've got that triangle mechanism holding it up there, so it should be pretty stable. And let's just run that the other way. Yeah, definitely agile enough there. Obviously at some point it'll overbalance, but it's got enough force there to... Oh, one of those is cool. Which way is it going? But anyway, we can move this in all directions, and it seems agile enough, which is really good. So I don't think there's going to be any difficulties. And the motors, of course, will be PID controlled and speed controlled with position feedback on the joints. So we should be in a position where we can accurately position them and stop them in the right place. And obviously not run them at full speed all the time, so as the battery goes flat we've still got some overhead where we can keep running those motors at the right speed. Alright, and the final weight of this comes in at 3.8 kilograms in Earth's gravity. So that's 1 foot and ankle. Obviously we need 2 of these. Now I have 3D printed all the parts at the same time, so I don't have to go and do all that work again, but I do need to wait for some more aluminium extrusion to arrive to put that together. But hopefully I should have that done by the start of the next video, and at that point we can then work on the upper legs and start thinking about that hip mechanism. Now that needs to be slightly different because it has the extra axis where the feet can rotate slightly so it can turn on the spot. So we have to think about how that's going to work and how it's cross-braced so there's not too much wobble in it. And I want to do that slightly differently to the way I did it last time. So don't forget to subscribe for more updates on this project and other projects. And also you can check out my Patreon campaign at patreon.com/XRobots, where you can get access to some exclusive rewards, including all my videos early. You should also check out my Spreadshirt store for exclusive t-shirts. I have a limited edition design which expires at the end of January 2017, so there's only a limited time to get them. Alright, that's all for now.